of us had
So
many.
today 12 p.m.
Yes, sir, that will work fine, sir.
Okay.
Yes, sir. Yes, sir. Thank you, sir.
All right.
Thank
all
you,
right.
sir.
After the class, I'm increasing it.
Okay, sir. Thank you so
Yes,
much, sir.
thank you, sir.
All right. So today we'll study the logic minimization. It's Quinn-McCluskey method. You will see why it is called two level. Just to mention, there can be even more levels of logic optimization. We are just doing two level. There are more complex methods for doing multi-level logic minimization. Okay, so this is a tabular method in the sense that you can write a systematic program with a data structure of a table to solve this. Let me explain with an example. So what we'll do, let's say, then I'll come back to the steps. Okay, so let's say you are given a logic formula, a logic expression. Let's call it A. There are 4 variables, A, B, C, D. And these are the min terms. So it's a sum of product from. So the min terms are 0, 5, 8, and so on. And you can know you know that these min terms, they have you can write them as equivalent logical form. So if for example, if you take the min term 8, it will be 1, 0, 0. It's just the binary number for 8, binary representation of 8, 1, 0, 0. The way to interpret it is that the min term number 8 correspond to the value of ABCD 1, 0, 0. 1, 0, 0, 0 is the corresponding value of ABCD is 1, 0, 0, 0. Okay, so that's how we numbered the min term. So basically, you convert the min term number to binary, and you get the logic assignment to the variables. In this particular case, we don't have a don't care. We only have the min terms. So what I will do is that, let me take another slide to explain. Let me take a new slide. What we will do, so what are the min terms that are available with me? Let me check. What are the min terms that are available with me? Wait a minute. Or maybe let me take this. This is better. Okay. Let's take this example. So we have this function f2. We have this function f2 consisting of the variables w, x, y, z, and these are my min terms. So what I will do, if you write all these min terms, so I have 0, 1, 2, 5, 7, 8, 9. I have listed all the min terms here. I have listed all the min terms here. I have written their corresponding binary representations, the assignment values for w, x, y, z. So I group these min terms based on how many ones they have. So for example, this is one group. I'll explain what this tick and everything means later. So I group, so this is a group consisting of 0 number of ones. Only one will be there, obviously. 1 to 8, 1, 2, and 8, they contain a single one. 1 is 0, 0, 0, 1, 2 is 0, 0, 1, 0, and so on. They contain a single one. Similarly, these are the min terms which contain 2 ones. And these are the min terms which contain 3 ones. And obviously, there will be a single min term 15, which contain 4 ones. This table would have been more if you had more variables. So one reason why Quinn-McCluskey was introduced instead of Karnaugh map is that it's difficult to extend Karnaugh map beyond, say, 6 variables. It's become cumbersome. But this Quinn-McCluskey can be used for any number of variables, even for large number of variables. Okay, so I group this depending on how many ones the binary representations have. Now I look for matching pair from between one group, this min terms in one group, with the min terms in the next group. Okay, so 0, this group, I will compare, I will try to match with members of the next group containing only ones. But what is the matching rule? The matching rule is that you can match them if they differ in only one variable. So for example, 0 and 1, they are matching pairs because only in Z they differ. Similarly, 0 and 2, they are also matching pair because only in Y they differ. Similarly, 0 and 8, they are also matching pair because they differ only in W. Okay, so I create another table in step 2, same W, X, Y, Z in the column, but these rows will now contain these matching pairs. But this thing you try to remember, I am matching one group with only the members of the next, only the min terms in the next group. I'm not skipping these groups. I'm only comparing them with the next group. And I call them matching if they differ in exactly one variable. So you can see the matching pairs are 0, 1, that is a valid matching pair, 0, 2, that is a valid matching pair, 0, 8, that is a valid matching pair. And these min terms 0, 1 to 8, if they appear in any of the matching pairs, I check them. I put a tick mark. I check them. I put a tick mark on them. And for each of these matching pair, I write down the W, X, Y, Z variable in the following way: is that only the variable in which 0 and 1 differ, I put a hyphen there, and rest I put whatever value was there. Okay, so 0 and 1, W, X, Y was 0, 0, 0. In Z they differed, I put a hyphen in Z. Similarly for 0, 2, they differed in Y, I put a hyphen in Y. 0, 8, they differed in W, I put a hyphen in W. So these are the matching pairs I get by matching the 0 group with the 1 group. Now I'll try to combine the 1 group with the 2 group. Note that these groups are formed by counting the number of ones in this binary representation. So I match this 1 group with the 2 group. So I try to match 1 with 5, 9, and 10. So is 1 and 5 a matching pair? Is 1 and 5 a matching pair? Yes. They differ only in X, 1 and 5. They differ only in X. So I put a hyphen in X, I copy the rest. I write down the 1, 5. 1 and 9 are the matching pair? Yes, 1 and 9 is also a matching pair. They differ only in W. I write down a hyphen in place of W and the remaining values. So 1, 9 I include. And what I do, I put a tick mark. So 5 is involved in this matching pair, I put a tick mark. 9 is also involved, I put a tick mark. 1 and 10, is it a matching pair? No, they differ in more than one position, so they are not a matching pair. Similarly, I look at 2 and 5, 2 and 9, 2 and 10. So you can see that 2 and 10 combines. They differ only in W. So I put a hyphen in W and 0, 1, 0 in the rest of the pattern. Similarly, 2 and 10 does not combine. 2 and 5 also does not combine. Do not match. 8 and 9 match. 8 and 10 match. I put them down. Okay. Similarly, next, what I do, I try to match this 2 group with the 3 group. 2, 1 group with the 3, 1 group. So 5 and 7, 5 and 13. 5 and 7, 5 and 13 match. I put this. 9 and 7 do do not match. 9 and 13 do not match. 10 and 7, 9 and 13 match. 9 and 13 match. 10 and 7 do not match. 10 and 13 do not match. I don't have them. And whatever is covered, I put a tick. I put a tick here. Now next 7, 13 with 15. 7 combines with 15. 13 combines with 15. They differ in exactly one position, so they are matching pairs. I put a hyphen in terms of the differing position, and I put the rest of the values, and I get this. So I put a tick across this. Okay, so this is my step 2 table. Step 2 table. Can anybody tell what each of these matching pairs mean in terms of the Cardano map? In terms of the Cardano map, what these matching pairs mean? Anybody?
We merge
So
those
they
two
can form a
blocks.
two-sized cube.
They are a two-sided cube. Very good. They are two-sided cubes. Okay. So now let's forget. Now look at the step 2 table. Look at the step 2 table. Now again repeat the same procedure. Like 0, 1, you try to match with 1, 5. 0, 1, we try to match with 1, 9. 0, 1 with 2, 10. 0, 1 with 8, 9. 0, 1 with 8, 10. So 0, 1 and 1, 5. Do they match? Do they differ in exactly one position? No, they do not differ. They differ in 2 positions. So including you also have to match the hyphens. You also have to match the hyphens. So 0, 1 matches with what? See, I'll only compare consecutive blocks. These I call them as blocks. And I'll only try to match consecutive blocks. So 0, 1 matches with whom in the next block? Matching means, again I repeat, only one bit position differs. Only one bit position differs, including hyphens. So 0, 1 matches with 8, 9. So in W they differ. In W they differ. Okay, so I'll write down this matching pair 0, 1, 8, 9, and the corresponding 0, 0 hyphen was there. So W is differing, so I'll put a hyphen in W also. So 0, 1 and 8, 9. So W position they differ. We'll put a hyphen in W, and the rest I'll copy. Similarly, you see that 0, 2 will match with 8, 10. 0, 2 matches with 8, 10. That also I write down. That also I write down. And again, I put a tick mark here. Whatever is part of a matching pair, I put a tick mark here. Now I try to match 1, 5, 1, 9, 2, 10, 8, 9, 8, 10 with 5, 7, 5, 13. These 2 blocks I try to match. And I get only one matching pair, 1, 5 and 9, 13. The varying variable, I put a hyphen. Rest of the things I copy, I get this. Similarly, next I try to compare 5, 7, this block with this block. And only 5, 7, 13 and 15 match. I put a hyphen and I get this pattern. Now in this step, so this is my step 3 table. In my step 3 table, are there any 2 blocks which match? Does 0, 1, 8, 9 match with 1, 5, 9, 13? No, it doesn't. They differ in more than one position. Does 0, 2, 8, 10 match with 1, 5, 9, 13? No, it doesn't. They differ in more than one position. Does 1, 5, 9, 13 match with 5, 7, 13, 15? No, they differ in more than one position. They are not matching pairs. Okay, so you cannot, expand this table further. Okay, so we have these 3 tables now. You find out the entries. You find out the entries in this table which are not check marked yet. Which are not check marked yet. So you can see everything in step 1 table is check marked. Everything is okay. By the way, what does these matching pairs correspond to? 0, 1, 8, 9 in terms of the Carnot map. What do they correspond to?
4-sized cubes.
4-sized cubes. Very good. After stopping, I'll pick up all the entries which are not check marked. So in this case, it is only these 4 entries which are not check marked yet. Only these 4 entries which are not check marked yet. So each of these entries which are not check marked yet, they I'll call them as prime implicants, and I'll write down the min term, or I'll write down the logic expression for them. So this is, so I have 4 prime implicants. Let's name them A, B, C, and D. So what is A? What is A? This is 0, 0. So A is x prime y prime. What is B? B is x. I dropped the hyphens. I dropped the hyphens. B is x prime z prime. B is x prime z prime. C is y prime z. C is y prime z. D is xz. D is xz. So this is my, this A, B, C, D corresponding to this terms. These are my set of prime implicants. Let me call that set as P. These are my set of prime implicants. Okay. Can anybody tell me why these are prime implicants? Why these are prime? What are prime implicants and why are these prime implicants? Anybody? Anybody? Why I'm calling? Why are these? Do you know what is a prime implicant? Can anybody tell what is a prime implicant? In terms of Carnot map, maybe. Okay, let us draw this Carnot map. These 4 variables.
So it cannot be reduced anymore?
Yeah, these are the largest cubes that you could have formed. Okay, these are the largest cubes that you could have formed. So let me try to. W X Y Z. Okay, so what is the sequence? What is the gray code sequence? Can anybody tell in this Carnot map?
0, 0, 0, 1, 1, 1, 1, 0.
One zero. So which are the min terms that we have for this function f2? What are the min terms that we have? You have this min term and 2, which is 0, 0, 0, 0, 1, 0. This is one we have, and then we have 5. 5 is which one? 5 is 0, 0. No, 0, 1, 0, 1, 0, 1. So this is one we have. 7 is okay. It is taking a lot of time. Forget it. So see, if you write down these min terms, you will see that these one are the 4-sized cubes, 4 cubes that you have formed. These are the largest cubes that you have formed. Tell me one thing. If I want to express this function f2, do I need all these prime implicants or a subset of them is enough? Maybe. Do I need all these prime implicants? Are all of them required to express the function? Or maybe a subset of them will do? What is your answer? So I have this four set of prime implicants because of this procedure. And my question is, somebody has asked me to minimize. So if I give my answer that the minimum form of F2 is this x prime y prime plus x prime z prime plus y prime z plus xz. So my question is this the minimum expression, optimized expression, just by adding all the prime implicants? Yes or no?
Sir, might or might not be the minimum.
Might or might not. Might or might not. So In some situation, this might be the optimal, and in some situations it might not. You can so in other words, the same function, you can take different subsets. It is possible to have different subsets of the set of prime implicants to express your function, and one of them will of course be the minimal. Okay, so next what I will do, so now that I have got my set of, this is what I have got after all this procedure, the set of prime implicants, I will try to set some methodology so that I get the minimal set of prime implicants. Okay, so now let's go ahead. So I have this
Sir?
four, yeah.
Sir, could you please explain once more what these check marks mean?
This check mark means that this min term was already involved in another matching pair. This is absorbed in another matching pair. In other words, if you look at it like this, so that means this min term is part of this cube, is already part of this 2 cube. It is covered by this 2 cube. So check mark means it is covered by another term. It is covered by a cube. So you can think of this, each of these min terms as one-sized cubes. And these are 2-sized cubes. This tick mark means this one-sized cube is part of any one of these 2-sized cube. Okay, it's part of, it is covered by one of these 2-sized cube. Similarly, a check mark here, this is a 4-sized cube. Let's say this is a 4-sized cube. This means this 2-sized cube is covered by one of these 4-sized cubes. It's part of one of these 4-sized, is inside one of these 4-sized cubes.
Sir, then how is 0,8 check mark? It's not part of a single 4-sized cube.
0,8 is not
Okay,
part
sir,
of.
it's part of the first cube, yes, sir.
It is part of the first cube.
Okay, sir, yes.
You don't just look at the matching pairs as such. You look at that this entire term is a subset of this or not. Okay, so finally the unchecked part will be the cubes which are not covered by another cube. That's why they are the prime implicants. They are not completely inside another cube. They may have overlap with another cube, but they are not subset of another cube. Whereas the check marked ones are subset of a larger cube. So subset of a larger cube. Okay, so that's why I call it the largest cube. Largest cube means it is not a subset of any other cube. Complete subset of any other cube. Okay, so these are the prime implicants. So as you have mentioned that now let us try to find out the minimal set of prime implicants that we need. Okay, so we'll go ahead to our next step using these 4 prime implicants. So we'll now process these 4 prime implicants. Okay, one more thing I'd like to mention that I have written all the min terms in the previous example. If you have some don't care terms, you treat them identically as min terms. So these are some don't care terms I have. So you treat them identically. So you put this 1, 2, 1, 2. Don't care terms also you consider. You treat them as if they are min terms also. Later we'll discriminate them. So I slightly extend this procedure in the case where I don't care. The procedure is simple. If you have some don't care, just treat them as min terms and follow this procedure. Okay. Okay, so this is a larger example. This is how we'll get, and this is how we'll get, and finally you have some prime. Here you see, here is an example where there are smaller matching pairs that are not covered by anybody else, that are not check marked. You have smaller sized cubes or matching pairs which are not covered, which are not tick marked. Okay, so if you look at the final set of prime implicant, you see these B correspond to a 2 variable 4-sized cube, whereas these are these 3-sized cubes is which one is a three-sided cube? Which one is a three-sided cube? Where did I get a three-sided cube? Okay. No, sorry, I made a mistake. This A is a two-sided cube, this B is a three-sided cube. So this is A, this is B, and these are all these C, D, E, and so on. These are, you can see, they are four-sided cubes. Sorry, the two-sided cube, four variable prime implicants. Okay, so this is another example. So I think this is clear. So you follow this procedure. In the end, you pick up all the unchecked matching pairs, find out the corresponding logical expression, the min terms, and put them down and make them a set, and call that as the prime implicant set. Okay. So next you make a chart called the prime implicant chart. The rows of this chart are the prime implicants that you have got in the previous step. So A, B, C, D. Let's take the first example. So these are the four x prime, y prime, x prime, z prime. These are the four prime implicants you have got. Okay. And in the column, you write down all the min terms. So these are the min terms you had. You write them down in the column. Note that you are not writing the don't cares. You are only writing the min terms. Only the min term. This point you note down. In the earlier step, we included the don't care. Now you don't include the don't care. You write only the min terms in the column. Okay. So next, what you do, you see which of these min terms are covered by this prime implicant, then you put a cross. There you put a cross. Okay. So how do you find out that? So what does 0 correspond to? 0 correspond to 0, 0, 0, 0, which is W prime, X prime, Y prime, Z prime. W prime, X prime, Y prime, Z prime. So X prime, Y prime is part of that. So you put a cross. What is 1? 1 is 0, 0, 0, 1. It is W prime, X prime, Y prime, Z prime. X prime, Y prime is part of that. Put a cross. Okay, understood? Is this okay? Is the procedure okay?
Yes, sir.
Okay. So what I am basically doing is that I am writing down the variable expression for each of these prime implicants. Very easy to do. You get the decimal equivalent, and just if it is 0, put a complement, otherwise put the variable. So you get it, and you know the variables in the prime implicant list that we have. So for every row which is a prime implicant, you see it is a subset of that min term or not. It is a part of that min term or not. If it is so, you put a cross. And this we would call a prime implicant chart. Prime implicant chart. One part you look in the prime implicant chart is that because of the nature of the prime implicant, every column has at least one cross. Every column has at least one cross. It has to have at least one cross. Otherwise, because of that matching pair previous rule kind of thing, every column has to have one cross. Okay, one more thing, let me tell. You look at the columns which have only one cross. Look at the columns which have a single cross. What is the meaning? Meaning is that, for example, take the column number 2. Take the column number 2. There is only one cross in the column number 2, and that cross corresponds to B, the prime implicant B. So that means in the final logic expression, if you want to cover min term number 2, you have to have prime implicant P. Otherwise, you cannot cover min term 2 because that's the only cross you have in that column. That's the only cross you have in that column. So I have circled them actually. So if you want to cover min term number 2, you have to have prime implicant B. If you want to cover column min term number 7, you have to have prime implicant D. If you want to have column 10, you already have B. If you want to have cover column min term 15, you have to have D, which you already have. So this B and D has to be there in the final expression, and this we call as essential prime implicant. Essential prime implicant. So B and D would be called the essential prime implicant. Okay. So if you look at the final expression for F2, B and D has to be there. So X prime, Z prime and XZ, this has to be there. Okay. And this part is non-essential. This part is non-essential, and that you can have multiple ways of doing. So here is two possible ways of doing it. One is okay. So see, the whole idea is in this prime implicant chart. In this prime implicant chart, you have to choose the minimum number of rows which covers all the columns using these crosses. So okay, let me maybe I should have given this definition. Is a row is said to cover a column if that particular row has a cross for that column. So B covers 0, covers 2, covers 8, covers 10. So B covers 0, 2, 8 and 10. Similarly, D covers 5 and 7 and 15. So this is a cover. Okay. So the problem is choose the, so it's a kind of a optimization problem I give you. So I give you a matrix. And this let me call as P1, P2. These are the prime implicants. P3, and these are the min terms M1, M2, and so on. So what I want to do is, and there are some crosses that what are the min terms contained in the prime implicants. So I want to cover all the columns using at least one cross, using the minimum number of rows. Using the minimum number of rows, I want to cover all the columns with a cross. Covering means there should be at least one cross in that column. Okay. One corollary of this is that the columns which have a single cross, the corresponding row, the corresponding prime implicant are essential prime implicants. They have to be there in the final expression. So what I will do is, suppose I have chosen a subset of the rows which are enough to cover. So finally what I'll do, because every row is a prime implicant, there is a logic expression for that. I'll just combine them. I'll add up all of them and to get my final minimized expression. Okay, so the first step for this minimization is that this is a two-step minimization, because I'm looking at only two steps. I could have a prime implicant over prime implicant, second, third level also I could have done. So you as a first cut, what we have seen is that the essential prime implicants has to be there. Now I ask you the question, how should I choose the remaining prime implicants? Non-essential prime implicants, such that all the columns are covered. Essentials are anyway there. You cannot do away with them. So that's fixed. So what are the non-essential prime implicants that I choose?
So we can iterate over the rows, and then in each row we will go for each column. And if there is, like for every column of a row, if there is another implicant that covers it, then we can eliminate that row.
You can eliminate that row. Okay, so maybe what you are saying, let me try to write down. Let me try to write down. let's say these are my main terms. So let's put some values: M10, M9, M15, M3, M4. And let's say these are my prime implicants: P1, P2, P3, P4. Okay. And I have some crosses and everything. Let me first write down the essential prime implicants. So maybe I should put some numbers here. Yeah. Okay. So what are the essential? Am I audible? Hello.
Yes, sir.
Yes, sir.
Yeah.
Now you're audible.
Yeah. Now I'm audible. Let's say this is a prime implicant chart. So if I want to reduce this chart, can you tell me what can be a reduced chart? Because P2, P3, I know they are essential. So in my final logic expression, the essential prime implicants, P2.
So P1 is also essential, right?
P1 is essential. Why? Because what are the? Oh yeah, P1 is
Yes, sir.
essential. Okay. Let me modify it a little bit. Let me put this. Okay, P1 is no longer essential. So P2, P3 are essential. So they anyway have to be there. What about the rest? Non-essential. So I modify this chart as follows. So P2 is there. So M10, M3 I have already covered. M10, M3 I have already covered. So if I draw a reduced prime implicant chart, I don't need M10, M3 because it is already covered by P2. P3 similarly covers M9 and M3. So M9 and M3 also I don't need because P3 I have already covered it. So I am left with only M2, M15, M4. Because these I cannot do away with, these are essential. And P2, P3 are prime implicants, essential prime implicants. So P1, P4. What about P1, P4? So to find out what this non-essential part is, it is enough to consider this reduced prime implicant chart. Is it so? Because see, let me tell my final goal. Final goal is to I have to pick up certain rows so that using the crosses I cover all the columns. And I say P2 row number P2 and P3 are essential. They have to be there because there is only one entry in the corresponding column. So if P2, P3 are there, some other columns are also covered. So they are already covered. So the columns which are not covered yet are M2, M5, M15, M4. And there are two more prime implicants I can choose from. They are P1 and P4. Now, what is the structure for this? I have a cross here, M15, I have two crosses, M4, I have two crosses. So now I have to choose a reduced number of rows so that I cover each column. So what are my possibilities? Which row should I, which subset of row? So I can choose either P1 or P4. I can choose I. So one possible implementation is P2 plus P3 plus P4. Another possible implementation is P2 plus P3 plus P1. Because using either P1 or P4, I can cover these remaining three columns. Is that okay? So the same thing, I'm again trying to cover up the columns with the rows. Is it okay? Or
Yes, sir.
so this method is formalized by something called a Petrik's method. Achha, one more thing, if you have don't care, as I have said before, they need not be considered in this prime implicant chart because there is no compulsion to cover them. There is no compulsion to cover them. Okay, so this is I'll talk about a method which is the prime implicant method. So let's take this. Let's look at this. My example is too small to explain. My example is too small. Okay, let me try to explain it. So let us look at each column. So it can be covered by either P1 or P4. Column M2, I can cover it by either P1. So let me write it as non-essential prime implicant. Let's see how I find out them. This is the Petrik's method. So M2 I can cover by either P1 or P4. M15 or maybe, okay, this is a trivial example till I'm doing it. M15 can similarly be covered by either P1 or P4. Similarly, M4 can be covered by either P1 or P4. So this is a very trivial example. In general, there can be more examples. Let's take this example. Okay, so column 0, column for prime implicant for min term 0. What are the prime implicants I need? H plus I. Column 1, what are the prime implicants I need? G plus I. Column 4, F plus H. Column 20, E plus F. Column 22, D plus E. Can you tell me why I am connecting them by a product? Why I am producting them?
All of them
because all the min terms are
all of them has to be covered. Okay, so what I will do now, note that this is the I have removed the essential part. So this is the essential part that I have removed, and this is the non-essential part. Essential part anyway has to be there. Non-essential part I have drawn a reduced prime implicant chart, and on that I am writing this expression among the prime implicants. Okay. All right. So what Petrik's method will do? Is that it will expand this by applying the distributive law of Boolean algebra. It will expand this by applying the distributive law, and it will apply this rule to do a reduction. It will apply this rule to do a reduction. Okay, so if you just have, so it is distribution followed by this reduction. If you do that on this formula that I have got here, it is very trivial. Let's say this formula that we have got, you will get a reduction. So earlier it is a product of sum form. I have now got it a sum of product form. From this sum of product form, can you tell what can be the non-essential prime implicants? What are the non-essential prime implicants? So the essential part you see, A and B, these are the essential parts. These are there. These are anyway there. Okay. What can be the non-essential part? So can you tell me how do I pick up the non-essential part from this sum of product form?
Sir, can we choose any of the term which contains the?
You can any of the form, because you see that this is a OR. So if you pick up any of this will cover P. If you pick up any, since this is a OR, if you pick up any of this, it will cover P. Okay, so you could have chosen any of these. So your possibilities are either you choose EHI or EFI or DFI or EGH. Can you tell me why I have left out DFGH? So all of these are equivalent. All of these are valid formulas. Why I have left out DFGH?
That contains strictly more terms than the others. So
that contains strictly more terms. So that's not a minimal realization. So I am reducing the number of terms. So these three are the minimal realizations. So this method is known as the Petrik's method. This is a rather simplistic view of things. This is a rather simplistic view of things. What has happened? This is a rather simplistic view of things. In actual practice, you choose among these also, possibilities also, by considering other factors as the number of gates you are using, number of, if you are using CMOS, what type of operations are costly, what is the power requirement, what is the interconnect requirement, what is the wiring requirement. So you have several other considerations to choose one among these. But those are more detailed. I mean, you need to go into power analysis or geometry analysis to the layout analysis to all those things. Now, we are not going into all this. We are just staying at the logic level. We are not going to the physical level. Okay, so this is the process. This is how minimization is done. Oh, again, I should repeat, this is a two-step minimization. I'm first finding the prime implicants. Then I'm finding the essential prime implicants. Then I'm finding the minimal non-essential prime implicants. And I could have gone further. I could have kind of note that this method does not guarantee that this is the smallest realization possible. There is no guarantee. This is the minimal realization possible. Okay, so I could have done other way. I could have gone to higher level. I mean, among the prime implicants, what are the non-essential prime implicants which cover all the prime implicants? So I could have imagine these as min terms. Imagine these as min terms, and then do you have a meta prime implicant to cover these min terms? Those analyses, again another round of Quinn-McCluskey I could have gone through. But those are more computationally intensive. But the procedure is same. You go to higher level things. So this is the thing. And most of the CAD tools, since this is also sometimes called a tabular method, and it's easy to implement in terms of a data structure and loop. So this is a method that is implemented in all CAD tools. Okay, thank you. Any other questions?
Sir, so how did you arrive from P equal to H plus I into G plus this product to the second line, EHI plus EFI?
I have just multiplied them.
But sir, the reduction from line 1 to line 2 is not trivial. Like, we'll have to notice some things. And
yeah, so you repeatedly apply this. Yes, I missed that. Okay, so what you do is that you have to apply this reduction. You try to multiply two terms which have common prime implicants. So these two you multiply. So can you tell what are the pairs which will try to multiply so that we can do a lot of reduction? What are the pairs will multiply? So H plus I into G plus I will multiply because there is a common prime implicant. Similarly, I could have multiplied these two. They have F as common. Or I could have multiplied these two. They have E in common. Yeah, you are very right. So we will not consecutively multiply the pairs. We will form a multiplication tree such that you multiply two sum terms which have one argument in common, one prime implicant in common. Can you tell me why I am doing that? So what is the advantage if I multiply H plus I into G plus I? What I get?
I plus GH, sir.
I plus GH. I plus GH. I plus GH. What happens if I multiply? Why is this good for me? I plus GH. What happens? What is the advantage I get?
Fewer number of terms.
In the subsequent step? Do I get any advantage? Do I get any advantage? What about if I multiply f plus h into e plus f? I get f plus eh. F plus eh. Okay, one thing is, yeah, you get less number of terms, but does it? I have just missed this part. Does it help me in reducing to this form somehow? Help me in applying this. Oh, this I have already applying. Sorry. Yeah, by virtue of this, I am getting this from this. By virtue of this, I am getting this from this. Fine. Yeah, okay. So it's simple. So you apply this rule, you do this multiplication, you get this term. You get this term. So you look for pairs which have one prime implicant in common. Okay, so these are reduced. So subsequent multiplications will lead to smaller terms. Right, you are right.
But sir, like implementing this through a computer, automating this process is not simple. Like we can do it, but the algorithm will be not very straightforward.
So if you are given the set of these sum terms, what you have to do is you have to identify pairs of sums which have terms in common.
Yes,
okay.
Sir.
And
So means there is an easier way by looking at the table itself to.
Is there an easier way? Is there an easier way?
I think there is.
What can you say? What is the? Yeah, there should maybe an easier way. What do you suggest?
Sir, what we can do is that we have 6 columns, 6 rows in the reduced prime implicant chart. So we can iterate over all the rows, and then for all the rows, we can iterate over all the columns and check if any other column has X. So that row, if that is true for every column of that row, then we can remove that row itself.
Okay. Yes.
So in the end, whatever will remain, it will automatically become essential.
But will you give all these answers? Will it give you all these answers?
So what we will get will automatically be the minimum because we are removing everything that is unnecessary.
If there are multiple minimums? In this case, I have 4 minimums.
So we'll get any one of them. We'll get any one of them.
Yeah, I think I'm not sure. I'll check up and tell you. Probably in the CAD tools, they want to have all these minimums. And because then they will provide other consideration. They will have other considerations, maybe power or time or something. They will have other considerations. I think I'm not exactly sure. Maybe they look for all these minimal realizations and then choose among them. So I think that's why they go for this metric method.
Yes, sir. So if we need all these, then we cannot use that method. We'll have to do this.
I think that's what they know. I'll tell you, maybe you can also think of, basically you need an algorithm to convert a sum of product of sum to sum of product. Disjunctive normal form to conjunctive normal form. So that's what we need. There are standard algorithm, I'm forgetting it right now. I think there are standard algorithms for doing that. One trick I forgot to mention is that you look for pairs, you look for sum terms which have prime implicants in common, so that you can apply this rule. So that will lead to reduction. But I think this should not be. You can have a data structure to do this multiplication. You can arrange it in a data structure and do the multiplication. Just think about it. There are standard methods. I mean, there's no doubt about it. There are standard methods for doing it. You think on a bit. In fact, I had written the code once. Long back, I had written this code, convert, but I'm forgetting the steps. You can check out.
Okay, sir.
Okay. So any other question, anybody?
Sir, a gentle reminder for the deadlines.
Yeah, I'll do it. I'll do it.
Yes.
Right now, I'm doing it.
Okay,
right now, after the class, I'm doing it. Okay, thank you then.
And sir, could you also upload the previous slides on WBCM?
You mean the Boolean algebra slides?
Yes, sir. Whatever we covered in the last few weeks.
Oh, okay, I'll do that. I'll do that.
Thank you, sir.